This is lecture number 5, and we're talking in this lecture about system responses, time responses, and frequency responses. That's what we're looking at in this lecture. So we have seen already that we have a variety of signals that appear in our system. Some are continuous time, some are discrete time. This one is piecewise constant, a variety of signals. And now we want to be able to work with this as a system. So here we are in our list of topics. We have the difference equation we talked about and the H transform. Then we have discrete time systems that we're going to be talking about, and that's what we're going to be looking at here. So that's our topic. So what is a system's characteristic response? What is a system's characteristic response? So we can talk about that in terms of the time domain, or we can talk about it in the frequency domain. In terms of the time domain, we could talk about the impulse response or the step response. Those would be good ways of looking at the system's characteristic response. In the frequency domain, we could look at the response. Basically, that's the response of sinusoids of the system to various sinusoids of various frequencies. Okay, so in the time domain, we have the question, how do pole locations affect the overall response? That's the question. So this is similar to situation as with the signal. That is, if we're just looking at a signal, the signal in the Q domain or Laplace domain or any transform domain is going to have poles. And those poles will affect the response of the system. Okay, and so in this case, our system now is being affected by an input, and the result is a rational function in Q as well. So this is also a signal. It will also have poles. So the real question now is, how do the poles affect the response? So we've just asked that. We're going to ask it again, or we just asked it again. Okay, well, let's look at simple signals and the response that they have. So here is a simple signal, a delta function. So that's 1 at time 0, 0 everywhere else. When you take the Q transform, Laplace transform, Fourier transform, basically you get 1. So all the transforms, we get 1 for a delta function. So as a function 1, notice as a function of Q, it is a function of Q, but it's a constant function of Q. And the value is independent of Q. You have no poles and no zeros. No poles and no zeros. So with regard to the unit circle, the system has no poles and no zeros. So simple. All right, how about this function? This is a unit step function in discrete time. Okay, here is the Q transform for that, 1 over 1 minus Q. That has a single pole on the unit circle at 1. So notice that poles in the right half plane are not the issue. It's not an issue of stability. It's poles. How do the poles relate to the unit circle? So remember, in the Q domain, poles outside the unit circle, well, we'll see that in just a little bit. But here we have this pole on the unit circle, and it corresponds with a signal that neither decays nor blows up. Okay, so that's what we have in this case. Now here we have this function, 1 over 1 minus e to the minus at times q, or 1 minus alpha q, alpha being this quantity. And here we have a couple of options. We have a being magnitude greater than 1, here a being magnitude less than 1. So a being in the exponent. Alpha here, I'm sorry, a being negative or positive. Alpha being magnitude greater than 1 or less than 1. So if a is positive, this thing is a decaying exponential. So a being positive. A negative, this thing is a blowing up exponential. Okay, so we have that situation. Okay, so it either blows up or it decays to 0. So if we notice the pole location and how that relates, So the pole that's inside the unit circle is the one that's blowing up. The pole that's outside the unit circle is the one that's decaying to zero. And recall that when we had a pole on the unit circle right there in between, it neither blew up nor went to zero. Okay, so it was somewhere in between. So this is an exponential function or a geometric term. So that's how that pole affects. What happens if we have other poles along the unit circle, around the unit circle? So here we have a pair of complex poles on the unit circle. Here we have a pair of complex poles. Here we have a pair of complex poles. And so this is the function that we get for those. And so notice that we have a sinusoid, actually a cosine, frequency omega. Okay, and so we see that depending on what omega t is, that will determine how the sinusoid varies. So notice here the points are the values at the sampling times. So these little lines in between just kind of help illustrate what a sinusoid of that same, a continuous time sinusoid of that same frequency would be looking like. Okay, so we can think of this as being a sampled sinusoid, and so you can see how the frequency can vary. So notice here, this purple star corresponds to poles on the imaginary axis on the unit circle. And so notice that that is at an angle of 90 degrees. Okay, and so we get a point every 90 degrees in the sinusoid. So we get a point at 0, 90 degrees, minus 180 degrees, and so forth. And so you get these points occurring. Okay, for that sinusoid, and so for poles closer to 1, we have a slower frequency. So you can see slower and slower frequency the closer we get to the 1, the point 1. So this is how a sinusoid, this is how the poles on the imaginary axis look. They basically give rise to a sinusoid. So remember, if you have a pole on a complex pole, you also get its conjugate. So if one's on the unit circle, the other is also on the unit circle. Okay, now here we have real poles. And notice that these real poles are inside the unit circle. And this is the response that we get. So these are first order systems. So if you have a pole here, you basically get, because it's inside the unit circle, it's associated with something that's blowing up, but it alternates while it blows up. Here, this is in the right half plane, and it blows up, but it blows up in a smooth kind of way instead of an alternating way. So that's what happens when we have poles there. When we have poles on the unit circle, we've already seen what happens here. We get poles at constant value 1. Here we get poles that alternate between plus and minus 1. Okay, so we get those poles that alternate. If we have poles outside the circle, notice those are stable. So the poles associated with this alternate and decay to 0. The poles associated with this decay to 0, but do not alternate. They go smoothly. Okay, so that's what happens with real poles. With complex poles, notice now I'm keeping the angle with respect to the real line constant here. And we have these possibilities. So if we have it outside the unit circle, we get basically a decaying sinusoid. So it oscillates, but it goes to 0. So here I've, again, kind of drawn in a little bit what the sinusoid looks like that's associated with that. This pole, basically, on the unit circle, basically is a sinusoid that neither blows up nor decays. And the frequency of oscillation is exactly the same between these two. So the frequency of oscillation is the same. The frequency is related to the angle that this makes with the real line. And then this set of poles is inside the unit circle, and you can see it oscillates and it blows up as it oscillates. Okay, and so notice that when we have poles at this angle, we get a particular frequency, and you have these 3 cases that happen. If we change the angle now, then the poles do the same kinds of things. These decay, these stay constant magnitude sinusoid, and then again these blow up. And again, now the frequency has increased. Okay, the frequency has increased in going to a larger angle. Okay, and so for the various angles around the unit circle, we will get faster and faster sinusoids. So here we have another set, and so you can see I get fewer samples per period here, fewer samples per period at this angle. One more, we get that. So here in this case, well, we get fewer samples per period. Okay, so we still get the same kind of thing. This one decays, this one, the magnitude remains constant. Notice that because we only get the sample values, here I've drawn in what the sinusoid it looks like. It's hard to tell that that's actually what the magnitude looks like, but that's what it is. And so anyway, so this is what happens. This is how the poles affect the response. So remember, if you have now any function in Q, you do partial fraction expansion, each of the terms is going to have poles. And so you can see what the contribution of each of these poles is going to be. It's going to be either something that decays, something that remains constant, or something that blows up. And it's going to be a linear combination of those kinds of things that either decay, blow up, or whatever. So this is how poles affect the response. So we've talked about different transforms, and it's important to understand the different transforms and what they're used for. Fourier transform is basically of time duration from minus infinity to infinity, and it gives us a function of frequency duration from minus infinity to infinity. Okay, so that's how the Fourier transform works. This is only defined basically for signals that are stable. The Laplace transform can be used for signals that are not stable, and the Laplace transform basically in time, the way we use it, the unilateral Laplace transform, takes signals that go from time 0 to time infinity, and it returns a function s that is a complex variable. So s can be anything in the complex plane. Here, notice omega is from minus infinity to infinity. It's a real value. Here, s is a complex thing. If a function in the Laplace domain is stable, then it has the Fourier transform is equal to the Laplace transform when s is on the imaginary axis. Now, the Fourier series takes a function from minus infinity to infinity, like the Fourier transform, but this is the periodic function, not a stable function. It's a periodic function. And so this will have frequencies, and the frequencies will be integer multiples of 2 pi. Okay, so we'll have that. The discrete time Fourier transform also takes something from minus infinity to infinity in discrete time, and it gives us something with frequency from minus infinity to infinity. Again, omega being a real value. There's the discrete Fourier transform, which takes n discrete time samples and gives n discrete time frequencies. And then there's the Q transform, which is discrete time. It takes signals from 0 to infinity and gives us something in the Q domain. Where Q is a complex variable. So these are the various kinds of transforms that we work with. The primary ones, of course, that we work with are the Laplace transform and the Fourier transform. But we will also do a little bit with the discrete Fourier transform. Okay, so suppose we have this continuous time signal. This is a sinusoid that decays. Okay, you can see it decays slowly. It oscillates a lot for its decay. We look at the poles of this. We have this. Here are the 2 poles. We have 1, 0. So that's what this function gives. We can, based on this function, we can plug in various values of s. And if we do, remember s is a complex variable, so that has 2 dimensions, a real and an imaginary. When we plug it in, the resulting values are going to have a real part and an imaginary part, which it makes it difficult to plot because you have the input, the independent variable has 2 dimensions, the output, the dependent variable has 2 dimensions, and so you need a 4-dimensional plot, which is not easy to do. So we can take, for example, a magnitude plot for s is equal to, for s is a complex value, and we can plot the response. So this is what the response of this function looks like as we for various s. And here we're just looking at the magnitude, not looking at the phase. Okay, I can truncate the frequencies. When I truncate the frequencies, this is what I get. So here I've truncated it along the imaginary axis. So this is all in the left half plane. And then here I've applied a log, so the log of the magnitude, and this is what we get. And I now put log frequency in there, and so this is what we get when we use log frequency. And so here I just rotated the plot, so I'm looking along the log frequency axis. And so notice that this red line is the value of s along the imaginary axis. We've plotted it, and so that is the basis of the Bode plot. So the Bode plot is basically the plot of the function along the imaginary along the imaginary axis, where we're plotting the magnitude in dB and the frequency in a logarithmic scale. So that's what happens with continuous time signals that we've transformed into the Laplace domain. When we have discrete time signals that are transformed into the Q domain, we can do a similar kind of thing. So here's the same signal in discrete time. Here's the signal in the Q domain. So remember, in the Q domain, the unit circle is the stability boundary, and so here are the two poles and the 0. Notice they're outside the unit circle just barely. Okay, and again we can plot the magnitude of this versus Q. Remember, Q is a complex variable, so it suffers the same issue that the Laplace transform variable S has. So when we plot it, we can plot the magnitude. Okay, the magnitude of this versus Q. And so notice the red line is the plot where Q is on the unit circle. Okay, so now if we just truncate so that we're only plotting things inside the unit circle, this is what we have. Okay, and so here we've applied a logarithm to the magnitude. And so the question is, given a continuous time signal r of t with a sampled version r of kt, we have this Laplace transform, right? This is the definition of the Laplace transform. Notice that if we assume a sampled value, that is, if we assume that t is small, the sampling time is small, then this integral can be approximated by this summation. Okay, so again, we're assuming t is small, so dt now is the sampling time, and so that's the dt now, and so we get this Riemann sum. Okay, so notice if I take this t out front, the rest of this is what we've defined to be r of q. So remember, q is equal to e to the minus st. Remember that? Q is equal to, so that's a unit time delay. Okay, so that's why this becomes r of q. So r of s is related to r of q through the sampling time t. Okay, so you need to use the sampling time t. So if I were to take that function r of s and I wanted to do a Bode plot of it with r of q, so r of q coming from this, I need to incorporate the sampling time in order to have a valid comparison. So here's what happens when we actually do that Bode plot, and you can see the two line up pretty closely. So the green is the discrete time version. The red is the continuous time version, and so we can do this Bode plot. Okay, and so we can do these comparisons, and so this shows that the two actually line up pretty well. Not exactly, not perfectly, and it's understandable that they wouldn't be perfect, and the main reason being that that one is discrete time, one is continuous time, but in a lot of the frequency range, they're identical. Notice that in discrete time we get this line that appears in our Bode plot. That line basically is associated with the Nyquist frequency. So basically our Bode plot is only really defined up to the Nyquist frequency for discrete time. So that's what we have. So how would we actually compute that frequency response? Well, here's one way to do it. We're given the discrete time sequence r of kt. We can compute an estimate of the frequency response of that sequence using the fast Fourier transform, the FFT. So So here we can actually plot this directly because we know what R of S is and we know what R of Q is. We know the formula for it, and so we can actually plot that directly. But if you don't have the function exactly, but you just have the data, then you can use the fast Fourier transform to compute an estimate of the frequency response. So this is basically the discrete Fourier transform. Now the reason it's called fast Fourier transform is because it turns out that if the number of data points is a power of 2, then there is an efficient algorithm for computing it, and that's called a fast Fourier transform. So that's what the FFT is about, but it's basically just the DFT. And so we can estimate the frequency response using the FFT. And we will show this a little bit later when we talk about how to do MATLAB for this class. So we've looked at time responses, we've looked at frequency responses a little bit. We now move on to talk about stability tests. So for discrete time systems, we have the stability of discrete time systems that we're looking at now. So if we first talk about polynomial, we know that the denominator polynomial determines the stability. That's where the poles are located. So we need to understand what exactly is a root of a polynomial. Now, that might sound obvious, but sometimes some things are not as obvious as you might think. So a value lambda is called a root of a function p if p evaluated at lambda is 0. Okay, so another way of saying it is it's a 0 of the function. Okay, so that is the definition for a root. You plug it in, you get 0. Okay, so here's a fact. And this is a fact from complex variables. Actually, this is a fact that's closely related to something called the fundamental theorem of algebra. Usually students are familiar with the fundamental theorem of calculus, but the fundamental theorem of algebra is what explains this next property. If lambda is a root of the polynomial p, then we can factor p this way. That is, we can factor, so notice that if q is equal to lambda, then this term is 0, right? 1 over lambda times lambda is 0. I'm sorry, is 1 times minus 1 is 0. So p is a root of this polynomial, then we can factor it this way. Okay, that is, there is some polynomial p1 such that this is equal to each other. Okay, so this is an important property of polynomials, that if we have a root, then we can always factor out this term out of the polynomial. So by way of example, here I have this function, and this function looks like a rational function. I have 1 minus q in the denominator, so it doesn't look like a polynomial, but we can actually show that this is indeed a polynomial. So we take the numerator, we call that p, okay, and we plug in the value 1 into p, and what we find is when we plug in 1, so notice q to the 1 to the 15 is just 1. We get all of this, and we can see that all of this adds up to 3 minus 3 is 0. So what this shows is that lambda is actually a root of p. And since it's a root of p, we can factor it. So p over 1 minus q can be factored as 1 minus q. So in this case, lambda is 1, so 1 over 1 is just 1. So we can factor 1 minus q, and the 1 minus q's cancel, leaving p1, which is a polynomial. Now, we haven't seen exactly what p1 is, but we know that it actually is a polynomial. This is not a rational function because of that pole 0 cancellation. So even though it looks like it has a pole, actually the pole cancels, and we are left with just a polynomial. So if we have a polynomial, in this case we have an nth order polynomial in Q, how can we test to see if this polynomial is stable without actually, for example, plugging it into MATLAB? Well, a polynomial like this is said to be stable if all its roots in Q lie in the exterior of the closed unit disk. So you have the unit circle, everything inside is and the circle is called the closed unit disk. That's the way it's described in math. And then, so whatever's outside of that, then, if the poles are outside of that, then this polynomial is said to be stable. We will often have a0 be equal to 1, in which case the polynomial is said to be monic. So notice what happens if we evaluate p at the value 0. Notice the q's all being 0, those all go away, and we're left with a0. So another way of saying the polynomial is monic is to say that p evaluated at 0 is equal to 1. That's another way of saying the polynomial is monic. So what happens? So we will generally assume this is equal to 1. What happens if this is equal to 0? Well, if that's equal to 0, then we can factor q out of all of these terms. We can factor q out of all of these terms, and we'll have a resulting polynomial that has a1 as the first coefficient. But what's important to understand is that if you can factor q out of that polynomial, that means that polynomial has a root at q equals 0, right? That is, if we plug q, so if a0 is 0 and q is 0, then that means we have a root at q equals 0, which is inside the unit circle. It's in the unit disk. Therefore, if a0 is not 0, this polynomial cannot, if a0 is 0, this polynomial cannot be stable. Okay, so we automatically know that if this polynomial has that coefficient equal to 0, then our polynomial is not stable. So we all automatically know that. So that's why we can just assume that a0 is equal to 1. If not, we can always divide this polynomial through by a0, in which case we will get that. Okay, and that will not change the roots of the polynomial by dividing through by a constant. Okay, so that's important. So again, if a0 is positive, then this polynomial, we have this jury test. This is the jury is out on this one. No, so is actually named after a man named Jury, whose last name is Jury. He came up with this test. So what he found is that if a0 is positive, then this polynomial cannot be stable if any of the following do not hold. So if we plug in 1 for p, we need to get something positive. If we plug in -1 for p, we need to get something positive. And we need to have this coefficient greater than the magnitude of that. So notice a is positive, so we need to have this coefficient greater than that coefficient in magnitude. Okay, so this is the jury test. So we have a polynomial here. Okay, so by just looking at that polynomial, it's not obvious to me whether that has roots inside the unit circle, on the unit circle, or outside the unit circle. So but we apply the test. We plug in 1 in here. So basically all the q's just become 1s. So we just basically sum the coefficients. 1 plus 2 minus 1/4 minus 1/2. All of that comes out to be 9/4, which is positive. Then we plug in -1 here. So basically, anytime we have an odd power of q, we get the negative sign. Anytime we have an even power of q, we keep the same sign. And so this is going to become a negative sign. This will stay negative, and then this sign will become positive. And when we add all that up together, we get -3/4, which is negative. So the jury test said I need to have both of these be positive, and so without going any further, we already know this polynomial is not a stable polynomial. I don't have to factor it. It's a simple test. And this simple test is enough to tell us already that polynomial has roots inside the unit circle. So if we actually did this, here's another polynomial. Okay, so this p evaluated at 1 is equal to 1. That's positive. P at -1 is equal to 2. That's positive. This coefficient is greater than that coefficient. So this polynomial passes all 3 of those tests. And so this shows that it's not sufficient, because if you actually calculate the roots of this polynomial, this is what we get. Okay, and these are inside the unit circle. Okay, these are inside the unit circle, And so this polynomial passes the jury test, passes the three conditions, but yet it's not stable. So this shows us some important things. First of all, it's necessary. The jury test is necessary but not sufficient. That is, a polynomial cannot be stable unless it passes the jury test. It's simple but not complete. It's a simple test, but a polynomial, like we just saw, can pass the jury test and still be unstable. However, it turns out it is both necessary and sufficient for a second-order polynomial, but not for a higher-order polynomial. So the jury test works for a first-order polynomial and a second-order polynomial, but it doesn't work for a third-order or higher-order polynomial. So what can we say about polynomials of different orders? Well, for the first-order polynomial, monic polynomial, it's clear this will be stable if A has magnitude less than 1. So remember, for A to have the root of this is going to be when Q is equal to minus 1 over A. So if A it has magnitude less than 1, then 1 over A is going to be outside the unit circle. Okay, and so this polynomial will be stable if magnitude of A is less than 1, unstable if magnitude of A is greater than 1, and marginally stable if the magnitude of A is equal to 1. What about second-order polynomial? So here's a second-order monic polynomial. I have two coefficients, A1 and A2. Notice that A1 is named this way because I have Q to the power 1, Q to the power 2, so that's why I call that A1, A2. So the jury test actually gives these two conditions. Those three tests boil down to these two conditions. One must be greater than the magnitude of A2. We saw that that's actually one of the conditions from the jury test. The other conditions, the other two conditions combined, give this condition. 1 plus this coefficient must be greater than the magnitude of A1. Okay. Also, the system is marginally stable if the magnitude of A2 is equal to 1 and the magnitude of A1 is less than 2. Otherwise, it's unstable. So we have complete results for a second-order polynomial, and we can actually plot those results in a A1, A2 plane. That is, anything within this triangle is stable. Okay, and here this green line shows this edge corresponds to a polynomial with roots on the unit circle, both real. One of the poles, or one of the roots, will be at Q equals minus 1. Okay, so if I have anything along here, I will have two real roots. This will have two real. Notice that since it's a second-order polynomial, if one of the roots is real, then the other must also be real. Okay, the only way you can get complex root is if you have its conjugate as well. So if one of the roots is real, then there are only two roots, so the other must be real. So this is when we have two real roots. One of the roots is at minus 1. Here we have two real roots. One of the roots is at positive 1. Notice here I have a root at positive 1 and one at negative 1. If my A1 is minus 1 and my A1 is 0, this is 0, and A2 is minus 1. So 1 minus Q squared is what I would get. And that has roots at minus 1 and positive 1. So along here, this corresponds to having complex poles around the unit circle. Okay, and any place in the middle here will give me roots that are in a stable region outside the unit circle. For a third-order polynomial, I have three coefficients, and we can go through and show that these three conditions are both necessary and sufficient to check for stability of this polynomial. Okay, both necessary and sufficient. Okay, so this is actually a complete set of equations. I'm not going to tell you where I got them. I could tell you where I got them, but it wouldn't make any difference to you. But anyway, we have these three, and so notice I have three inequalities, three unknown values. So anyway, in the second order case, I was able to plot the region of stability, the region of parameters a1 and a2 for which I have a stable polynomial. In this case, it's a triangle. Okay, so for this polynomial, if I want to find the region of a1, a2, and a3 for which these three conditions are satisfied, well, you have three terms, and so you can't get a nice 2D plot. You get a 3D plot. And so our 3D plot looks like this. These are different views of that plot. And so you can see that anything inside of this contour is corresponds to a set of values of a1, a2, and a3 such that that polynomial is stable. And so you can see it's kind of got a little bowlish or a curvy-ish on top, and it's triangulish on the bottoms, okay, and so forth. So anything on this surface corresponds to having a pole on the unit circle. Anything inside corresponds to having all its roots inside the unit circle, outside the unit circle, in the stability region. So this is interesting to see, although it's not that useful. So when we talk about stability now of signals and systems, we use the concept of a stable polynomial to refer to that. So a discrete time signal or system can be represented by a rational function. So here's a rational function for a signal. Here is a rational function for a system. The stability of the signal or system is determined by the poles of that system. We've pretty much already seen that. So a definition of a pole then, a pole lambda of a rational function r of q, is a value of the function such that the limit as q goes to lambda of r of q, that quantity goes to infinity. So we saw that the definition of a root is similar, but it's the inverse. So here's a quandary for you. What are the poles of this function? Clearly they're related to these guys here, but this function has three poles. It's clear where two of them are. Where's the third one? I'll let you think about that. So this is the stability issue. Thanks for watching.